Quick review that hippos are super scary. And that, oh, that's the bird I was talking about. That energy relationships include predation, competition, and then the three kinds of symbiotic relationships, which are parasitism, one gains and one loses, mutualism, both gain, commensalism, one gains, one doesn't care. And we used examples of the worms in the hippo, the bird, which you just saw a picture of, that cleans the hippo's teeth, and then the fish that swims behind the hippo. Then we talked about food webs briefly, and then trophic levels, primary, secondary, and tertiary consumers feeding off of producers, and then decomposers and omnivores not quite fitting into any of the categories. Questions so far? So moving on, we use pyramids as a kind of a visual guide to looking at the trophic distribution. When we say trophic distribution, we mean the amount of something in each trophic level of energy, biomass, which means total mass of living tissue, and numbers of organisms. So energy pyramids, biomass pyramids, and pyramids of numbers. And a question you will see on the test, and I'm telling you that, I only tell you test questions when they are so frequently missed that I really don't want you to make the same mistake everybody else does. Here's the question. How do we use pyramids to represent the total amount of energy in trophic levels, biomass in trophic levels, and numbers of organisms in trophic levels? The most common answer I get on that question is this, and this is not the right answer. Sorry, I'll let you catch up. The most common answer I get on that question is, we use pyramids because there's more energy at the bottom and less as you go up. I know what a pyramid looks like. Some of you are still going to do that. Okay. Don't just tell me that a pyramid's bigger at the bottom and smaller at the top. The question is why? Why is there so much energy at the bottom and then less and less as you go up?
Because there's more producers around and there are more consumers.
Right, but why? See, she's doing it. You all want to do it because there's more here than there is here. I know. Why? It's okay. If you have, why?
The animals, or yes, the animals or plants that get the energy, use some of the energy.
Oh, I like it. They use, you know, the whole thing, conservation of energy, right? Can't be created or destroyed. But it can be lost. Okay. Elijah, can you tell us what you've done so far today?
I woke up.
Yep.
I got dressed. I made my bed.
Awesome.
I brushed my teeth. I ate a granola bar for breakfast.
Good, good. Granola bar. What are your first and second periods? English and math. Okay, so he just described a bunch of things he did. Which of those things cost him energy? Which of those things did he have to spend, like, you know, ATP on? All of them. Every single one of them. All of them, from waking up to brushing his teeth to whatever he did in English and math class. All of that cost him energy. Now, when Elijah leaves the building today and the bear catches him and eats him, does the bear get the energy that he used to brush his teeth? Does the bear get the energy that he used to do Geometry? Pre-cal? What are you in? Geometry? Does the bear get any of the energy he used to do any of the things he described? No. You're right about the rule of 10%, but all the stuff he described, bear's not getting that. He used it. What happens to that energy, by the way, if it can't be created or destroyed, and he's using it? What's happening to it, Ayola? It gets converted into heat, and Elijah convects. I don't remember. Anyway, he radiates. He radiates that heat into the atmosphere. The air takes it away, and it's gone. It's lost. It's lost. What is really the only thing Elijah can do with his energy that the bear would get? I'll give you a hint. It's something that he and you are still doing that I am done doing. He can grow. The only energy that the predator that eats you, you're not going to get eaten by a predator, but if it did, the only energy it would get is the energy that you use to build more of yourself. That's what it gets. And yes, you're absolutely right. It turns out to be almost exactly 10% overall that one trophic level passes on to the trophic level above, the rule of 10%. Good. So to put that sort of in writing, there is energy loss between levels because energy gets used for all the stuff you do, gets converted to heat and lost. Then we can also throw in kind of the fact that you're not 100% effective at digesting your food. And we can say that really the only energy you pass on to what eats you is the energy you use to put on more biomass by growth or storing fat or whatever. Essay question. Don't just say because there's more at the bottom and then there's less as you go up. Explain why there's energy loss. Now, there are differences. Each different way you can do one of these pyramids. Producers are always at the bottom, right? And we go up, primary, secondary, tertiary, consumers. We don't worry so much about decomposing. A pure energy pyramid, in other words, if you're just measuring exactly the amount of kilocalories or whatever that are contained in the living tissue of the organisms in the ecosystem, it's going to be pretty dead on 10%. That rule of 10%, you know, if we're measuring kilojoules, it's going to be pretty precise, 5,000 to 550 to 5. So let's revisit one of your ecological scenarios from your project, because this right here kind of explains one of the things that might not have made sense. One of those scenarios was humans tend to not like predators. We tend to, you know, fearing for our livestock and our children, basically go on killing sprees where we try to wipe out top predators. And the question you might have, thank you, is why was that so easy to do? Like, we hunt deer like there's no tomorrow in this state and don't even barely make a dent in the population. Just basically keep it from being horribly overpopulated. And yet in 20 years of going after bears and mountain lions and wolves, they're gone. Why is that? Well, why is that, Elijah? The fact that it takes this much of producers to support this much of tertiary consumers means there's less of them. Their numbers are way lower. I forget the exact number, but it's like it takes 100 square miles of African savanna to support, one pride of lions, one group of lions. That's because of this, because of the energy loss. Because by the time you get up here, if you're making your living up here, you're depending on a whole huge ecosystem below you. There's not very many of you. So killing one wolf, killing one bear is a much higher percentage of the population, right, than killing one deer is, because there's way more of them. So that brings in this scenario for sure. Don't write it down. You already dealt with that. Okay. So that was an energy pyramid. Biomass pyramid, very similar. And I guess if you just write that, I don't know that you need to draw a whole other pyramid, but just know that like different kinds of living tissue are, worth different amounts of energy. Fat, the same mass of fat is worth more energy than that same mass of carbohydrate. So it's not going to be perfectly 10%. It's going to be a little off, but it's still going to be very recognizably a pyramid. It's numbers where things get weird. If we're just tracking numbers of organisms, things can get a little different. They can be normal. They can be a pyramid. If we were talking about an ecosystem like meadow, we might have 2,500 grass plants supporting 1,000 primary consumers, supporting 300 secondary, supporting 50 tertiary, maybe. But they're not always pyramids. Can someone explain why that might be? What doesn't a pyramid of numbers, where you're simply counting the number of organisms, what doesn't that take into account? They could really throw this off.
Energy.
Okay. Neither did biomass, but that still worked. What's the big difference here? We're just counting numbers. Good.
There's no percentage loss, just like random numbers. There's not a percentage from going from grasses to primary.
Right, it's not following the rule of 10% perfectly, no, but neither did biomass. There's something fundamentally different. Something it doesn't take into account that'll really throw things off in certain ecosystems. No. What if there was a particular organism that was really, 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 really huge? Are they worth a lot of energy? Do they have a lot of biomass? But what number do we use in a pyramid of numbers for that very, very, very large organism? It's only one. And yet one huge organism can support a bunch of smaller ones, right? Can you think of a huge organism that routinely supports hundreds, even thousands of other organisms while it's alive? This is hard because you actually don't usually think of them as organisms, but they very much are. That would be trees. Yeah, we have a lot of ecosystems based on huge producers, don't we? That would be forests. And a forest ecosystem is going to look real different because there's not that many trees that it takes to support thousands and thousands of, think ants, squirrels, fungi, bacteria, other plants, growing vines, all that stuff. It doesn't take that many trees. And so we might have 75 trees holding up a whole mess of primary consumers. And then, of course, it narrows down at the top. But yeah, size isn't taken into account here, so they can be weird shapes. I would go ahead and draw at least that one. Still a great essay question. Why pyramids? You got to explain that. And then why are pyramids of numbers sometimes weirdly shaped?